Welcome to my YouTube channel. My name is Abdul Rashid Adao. Today, I would like to talk about my research and teaching experience. By way of introduction, I'm a chartered engineer and member of Institution of Mechanical Engineers, United Kingdom. Also, member of American Society of Mechanical Engineers. Okay, my research is in the general area of fabrication, characterization, and materials. So I'm well versed in engineering, all classes of engineering materials, including metals and alloys, ceramics and glasses, semiconductors like silicon, germanium, polymers, and composite. Also, I'm also into characterization methodology, that is, to characterize multi-scale mechanical behavior for a wide variety of engineering materials applied in high temperature, energy, optical, extreme, and biomedical applications. So in the field of manufacturing engineering, I'm also focused in mechanisms of advanced manufacturing processes such as additive manufacturing, precision engineering, biomanufacturing, and so on and so forth. So generally, the microstructure of a material influences the mechanical properties such as the hardness, elastic modulus, ultimate tensile strength, flexural strength, fracture strength, and so on. The mechanical properties in turn influence the mechanical processing that will be applied on the material, such as machining, casting, extrusion, shaping, and other mechanical processing techniques. Then the mechanical processing techniques will influence the performance of the engineering device, such as wear, fatigue, which are useful in predicting the lifespan of the engineering device. In terms of research skills, I'm well versed in nano and micro indentation techniques, which are useful to simulate manufacturing processes or the mechanical behavior of materials during their mechanical fabrication, which can also be used in nanotechnology and micro technology. Also, I can use optical, scanning electron, scanning probe atomic force microscope conveniently and confidently. Also, I have a vast experience in the usage of X-ray diffraction for phases and then generally for getting the crystal structure of a material, such as the phase qubit center or body qubit center or HCP and so on and so forth. I can also apply differential scanning calorimetry to characterize material thermal properties such as the glass transition temperature, melting point of a material or glasses and glass ceramics. Okay? And then in terms of the fatigue, I can perform both a conventional fatigue and also non-conventional fatigue test. So the one I've highlighted here is the non-conventional fatigue, which is useful in restorative dentistry to predict the in-service survival of a dental restoration. I can also perform micro and nano mechanical testing, such as the usage of the micro in situ SEM micro compression test using the micro pillars in order to find the micro compressive properties or micro tensile properties of material. So in mesoscale or macro scale, I can also use tension compression, okay, test in order to get mechanical properties of materials such as the Young modulus, the yield strength, flexural strength, contact fatigue. Also, I can perform grip test and vibration test. In the field of manufacturing, I can use computer numerical control machine conveniently, and also the universal testing machine to perform tension and compression, bending, flexural fatigue, and so on and so forth. Now, in the field of my precision engineering, I'll be able to precisely obtain good surface quality on silicon by way of background information. Silicon is very hard and very brittle. So conventional machining of silicon can lead to fracture. So, and the silicon is useful in electronic industry because it is used as integrated circuits in integrated circuits chips. So because of that, the service requirement requires thinning of silicon and then to generate high surface quality. So there is a process which is different from the conventional machining called ductile mode machining. This is a non-conventional machining in which silicon and other hard and brittle materials can be machined in such a way in a ductile manner such that extensive microfracture is minimized. So the idea of ductile mode machining is that by proper selection of machining parameters such as depth of cut, feed rate, and spindle speed, materials can be machined in a ductile mode in which the plasticity or plastic deformation becomes the mode of deformation rather than fracture. And once we have massive ductile surfaces, the polishing time will be adequately reduced. So, and this one can be, ductile mode machining can be realized in single point diamond turning or ultra precision grinding, and then the machinery for both, the machineries for both are very, very expensive. Therefore, there is a term called precision grinding. It is a finishing process to produce component with nanometric surface quality. Okay, this nanometric surface quality is, the surface quality is improved in order to reduce the polishing time. It is, and this one can also be carried out on a conventional machining tools. So in my research, I adjusted the spindle speed of the NC numerical control milling machine, in which the highest speed was 6,300 revolution per minute. I attached it with a high-speed jig grinder. So to enhance the spindle speed to about 70,000 revolution per minute up to 90,000 revolutions per minute. So, and that one will now give us what is known as high-speed grinding. So, I use that principle on silicon to generate an average surface roughness of 37 nanometer on general purpose numerical control milling instead of the special purpose surface grinder. And this is the optical microscope of the surface silicon surface generated, and this one is the SCM. You can see the ductile streaks that we talk about. What is ductile streak? I mean, it's about the flow of plasticity. You know that when you say plastic deformation, is just the movement of dislocation by slipping. That is SISLIPPING. So that is the basis for which metals deform plastically. So this kind of nanometric surface meets ophthalmic condition, and the surface or the research has been published in this journal and sold to the ophthalmic industry. Now, in the field of mechanical behavior of a material deals with the deformation and the fracture of materials under applied load. This deformation of material can be elastic deformation, plastic deformation, and in the case of a polymer, can be viscoelastic or viscoplastic. So these mechanical behaviors are influenced by the application of load, and the mechanical behavior of a material using the indentation. Indentation is just that you use an indenter in the form of a diamond or tungsten carbide or steel to indent surface, to indent on the surface of a material, and the indentation process is because of the resistance to indentation by the material that will lead into, that depends on the mechanical properties. That is, the resistance of the to indentation, okay, is influenced by the mechanical properties of a material. So because of that principle, the researchers have been using indentation techniques to understand mechanical behavior. Also, the mode of deformation in indentation can be likened to the mode of indentation in deformation in machining. Also, when fracture occurs during indentation, that fracture can also be likened to the occurrence of a fracture in machining or other manufacturing processes. So based on this principle, mechanical material behavior during indentations can usefully simulate diamond machining for the zirconia and lithium disilicate glass ceramics that I considered in this research. Now, these are my research outputs. One of them is that, you know, that in the field of plastic deformation, there are various types of plastic deformation. For metallic material, the mode of plastic deformation is by dislocation, initiation, and motion. However, for all materials at nanoscale or microscale level, they can undergo some form of plastic deformation if the applied load is very, very small. Therefore, all materials, regardless of their hardness and brittleness, can undergo a transition between plastic deformation to fracture if the applied load is very, very small. So that in this case, the indentation techniques can be used to simulate the material behavior and generate the required deformation, elastic and plastic deformation and fracture for the material. Now, for presintered zirconia. Presintered zirconia simply means that in the field of powder metallurgy, where you are trying to make a metal or a material from powder. So you are going to have powders, particles like this. Then you have a mixture of them. Okay, just like in the field or like you are trying to bake, you mix them with a binder. But in this case, we call it isostatic pressing. Then after isostatic pressing, we now subject it to high temperature, which is now known as um, centering. But in the case of presintered zirconia, zirconia particles are compacted together, and once they are compacted isostatically, they are called grain compact. Okay, grain compact. So in order to join these, because and it also comes with high level of porosity. You have some porous structure. So in order to combine all these things, all these particles together, forming a microstructure, we are going to use a sintering process at around 900 degrees centigrade. That sintering temperature is the one which gives it the name presintered zirconia. Now, after subjecting it to higher temperature, the presintered zirconia now becomes sintered zirconia. Now, the mechanical deformation in presintered zirconia is different from that of sintered zirconia. For presintered zirconia, the mechanical deformation process is king band. That is what I generated from the indentation studies that I conducted, nano indentation studies that I did. You can see what is kink band. Kink band is a plastic bucking process in which there is a generation of a parallel pair of dislocation on slip plane. You can see because the material still contains some porous structure, so there will be movement of atoms, okay, during indentation. You can see this arrow specify the parallel dislocation, and this one, the vertical arrow, specify the slip plane, because dislocation of a material occurs on a suitable what slip system, which consists of slip plane and slip direction. So if there, I mean, that is the plastic deformation of material occurs along a suitable slip plane. So for presintered material, zirconia, the appropriate plastic deformation is kink band, which is represented by this microstructure. However, the plastic deformation of sintered zirconia is dislocation, initiation, and interaction, which is similar to what occurs in the metals. That's why when they discovered zirconia, it was named ceramic steel. That is a ceramic that behaves like a steel. having properties similar to steel, like this one, plastic deformation. Another one is metallic steel can also transform from one phase to the other. And then at appropriate temperature, sintered zirconia can transform from tetragonal to monoclinic, and from cubic to from tetragonal to cubic, and before it melts at higher temperature. So that's why it exhibits some properties that are similar to metals. Okay. Also, these studies are the first of their kind, because I was the only one that discovered this king band for presinter zirconia and dislocation initiation and interaction for sinter zirconia. Another thing, another progress or another outstanding result that I obtained for sintered zirconia was the extraction of yield strength. Okay, in nano indentation, I developed another method to extract yield strength of sintered zirconia in nano indentation. Briefly, yield strength is characterized by the onset of plastic deformation. That is when the plastic deformation starts to take place. And then the lower the yield strength, the higher the ductility of a material. So that is, the material can easily be deformed plastically. So the conventional method of using of extracting the yield strength in nanodetection was to use a spherical indenter, okay, instead of the Bakovich, because there are so many indenters. You can use Bakovich indenter, as well as you can use spherical indenter. Spherical indenter is always made of tungsten carbide, while Bakovich is made of diamond. So if you use spherical indenter, you are going to generate micro stress and strain. That is, you are going to have the stress along the strain, just like the conventional stress strain curve. This is the stress and this is the strain. So there is a formula for the stress, which you can use, which is equal to what? The applied force over pi a squared. That is, the A is the radius, the contact radius between the indenter and the specimen. So, and the strain is governed by the normal, the change in the diameter or versus what? Original diameter. Original diameter, that is D of the, or this change in the length over the original length. So from there, you are going to generate the stress engineering stress strain curve, or what is known as engineering stress. So the first part here, where you have the beyond the elastic limits, uh, is characterized by the yield strength. So this is the conventional way of generating it at microscale. So in my own study or in my investigation, I was able to use Bakovich, okay, with another geometry to get the yield strength by when you have uh, a when you have sintered zirconia subjected or indented at different loading rates. So that loading rate can be converted into strain rate by a certain formula. So if you see, if you peruse this journal, that is Material Science and Engineering A 2014, the process is well documented there. So after you have done that, after you have converted it, loading rate to strain rate, then you can use Tabo relation and then continuum model. What do you call it? Pressure idealized yield criterion in order to get, this is what I use anyway. I use pressure idealized yield criterion together with Tabo relation, Tabo, this one, Tabo relation, Tabo relation, and then pressure idealized yield criterion and the strain rate sensitivity. Strain rate model in order to get the yield strength of a sintered zirconia in nanoindentation. And that was very the first time that relationship was developed. Now, in the field of glass ceramics, I investigated two types of, one is lithium metasilicate glass ceramics and lithium disilicate glass ceramics. And then I was able to establish that the plastic deformation for both of them are shear bands and strain hardening. The strain hardening process is one of the processes used to increase the strength of a material, such as increment in the yield strength or the tensile strength of a material. So, and once you have an increment in a strain strength, in the increment in tensile strength, you are at the mercy of reducing the ductility. So the strain hardening process that occurs in lithium disilicate glass ceramics and lithium metasilicate glass ceramics accounts for the brittleness of the material, because the material we undergo little yielding, okay, little or no yielding because of the strain hardening process. Now, based on the mechanical behavior, that is based on different forms of the plastic deformation that I developed, I was able to propose material removal mechanisms for both pre-sintered zirconia and sintered zirconia, as well as lithium metasilicate glass ceramics and lithium disilicate glass ceramics. And this one are some of the key features of the indentation. Another interesting feature of the lithium metasilicate glass ceramic is the phenomenon called sinking in. That is, sinking in effect occurs for lithium metasilicate, that is sinking in. And then and also we have piling up, that is accounting for the extrusion that we occur during processing. So you can have sinking in and piling up. So the piling up, led to the extrusion of materials. So indicating that the material can actually undergo ductile mold machining through extrusion. Also, the material will sink in, accounting for brittle material removal. So all these phenomena are well documented in these publications. Now, I conducted what is known as advanced mechanical behavior of material. That is, by partitioning a particular mechanical behavior into elasticity and plasticity in order to know the dominant deformation mechanism, so that deformation that dominates will now account for how it will be processed during mechanical processing. So for presintered zirconia, it has got the highest ductility. That is, its plasticity was higher than elasticity. That means it can be processed in ductile mode machining. Better than sintered zirconia. For the glass ceramics, there are 3 different fabrication methods: pressing technique, another one is centering, and the other one is by just heating the glass batches. So I found out that pressed lithium disilicate glass ceramics is rated most ductile, followed by sintered lithium disilicate glass ceramics, and the least is lithium metasilicate glass ceramics, which now account for the brittle fracture of lithium metasilicate glass ceramics. Then, for the first time, I also developed that the ductility of sintered zirconia reduced during strain hardening process, which was also similar to the metallic behavior undergoing strain hardening. So these are also published in these all these journals. Now, in the field of biomanufacturing, in which case we use the principle of biomedical engineering, combine it with manufacturing engineering in order to get a process of fabrication, a process or processes for both lithium disilicate glass ceramics and sintered zirconia. Both are used as dental restorations, and then in restorative dentistry, there are different processes that are applied. One of them is computer-aided design, computer-aided manufacturing, followed by sintering, polishing, sandblasting processes, not in a particular order. So I therefore explored all these processes by combining them together and investigated the optimal manufacturing process that met the dental surface quality. And what was the dental surface quality? The average surface roughness for bacterial plaque retention, that is, the bacteria cannot retain if if the surface is very, very low, okay, and the threshold is around 0.21, which is equals to 200 nanometer of average surface roughness. So the technique that I used was to combine surface engineering methods, manufacturing science, and analytical approaches in order to generate this surface quality. You can see the smooth surface quality generated from from lithium disilicate glass ceramics, and this one for sintered zirconia. And then both processes have been suggested to the dental practitioners, and they are being implemented. Now, after getting the manufacturing processes for the 2 dental ceramics, there was a need to test their performance, that is structural property, processing, then performance. So one of the ways to test their performance was the fatigue test. Okay, and then the fatigue test that simulates the intraoral cavity or what operates in the mouth is known as Hertzian contact fatigue, in which case the material is like in this order. So you have a flat material indented by another indented with a spherical indenter at different load, that is cyclic load, and different frequency to generate what is known as the SN curve, that to failure. So in this case, I use a phenomenon called low cycle, high load Hertzian cyclic indentation, simulating teeth grinding and then clenching, which is known as bruxism. Okay, bruxism, that is teeth grinding and clenching. So the different processes proposed in the previous slide were computer-aided design, computer-aided manufacturing, followed by polishing and sintering. Another one is computer-aided design, computer-aided manufacturing, followed by sintering. Computer-aided design, computer-aided manufacturing, followed by sintering and glazing. Another one is computer-aided design, computer-aided manufacturing, followed by polishing, then followed by sintering, and followed by glazing. So I only brought out the two because these are two extremes that generated the highest surface roughness and the lowest surface roughness. So you can see, based on this, you can see the surface morphologies. The proposed method, that is the computer-aided manufacturing, computer-aided design, computer-aided manufacturing, followed by polishing and sintering, okay, generates less severe damage. This one, in in comparison with other fabrication processes. So I also propose that mechanical assisted growth of surface asperities was the proposed fatigue mechanism for all the treated surfaces. Now, in the field of microtechnology or microscale mechanical behavior, I try to investigate the influence of applied load during microindentation on the mechanical properties, such as the hardness and the fracture toughness. The fracture toughness of a material can also be measured by indentation techniques. So when the load increases, there are two phenomena. It is either the hardness increases with the load or reduces with the load. So if the hardness increases as the load, okay, is increased, that is known as reverse indentation size effect. And if the hardness of the material reduces as the load with the load increase, that is known as indentation, normal indentation size techniques. And then because of this, we can say the hardness of this material is dependent on the load. So it is now equivalent to find the load independent hardness. So how do we now find the load independent hardness? By using some models that are available in the literature. One of them is the Meyer's model, which relates the load with the hardness in this form. So you can see this is the load versus the indentation size. So when you take log of both sides, you are going to get this Meyer's index. So if the Meyer's index is less than 2, okay, that is showing that normal indentation size effect occurs. If it is greater than 2, that means reverse indentation size effect takes place. So other models that can be used are indentation induced cracking, proportional specimen resistance model, modified proportional specimen resistance model, then the A's and Kendall model, elastic plastic models. All these ones will show different characteristics. So from these, you can see that the Meyer's and indentation-induced cracking models strongly support the rise phenomenon for this material. The PSR, that is the proportional specimen resistance model, and the A's and Kendall model, elastic plastic models, they obtain the consistent intrinsic hardness. However, by coupling elastic plastic deformation model with Tabor relation, it gave the best intrinsic hardness, okay, which was consistent with the one obtained from the continuum model. And this is, these results are published in this journal. So what we are saying now is that the best or the intrinsic hardness for this material is 4.84. Okay, that is pre-crystallized zirconia lithium silicate, and then this one 6.91 for crystallized lithium silicate. So this one are also published in this journal. Okay, moving on, I also did the same for lithium disilicate glass ceramics. I investigated the Vickers response of lithium disilicate glass ceramics to different loads. And I observed, or I obtained that the response was normal indentation size effect. I also applied the same methodology to find the intrinsic Vickers hardness for the two materials. So based on my findings, I was able to find that Meyer's model strongly supported the normal indentation size effect, and then the proportional specimen resistance model, A's and Kendall model, and elastic plastic models obtained consistent intrinsic hardness. But the best intrinsic hardness was obtained from the modified proportional specimen resistance, and then elastic plastic deformation model. Okay, obtained the best intrinsic hardness for the material. Then for the fracture toughness, I was able to establish that actually the fracture toughness of this material, okay, increases as the size of the extension of crack extension increases. And so once this phenomenon occur, it is suggested not to use single fracture toughness number because of the because it fluctuates or it increases with the crack extension. So, and then this result can be found in this journal. Now, moving on, I intend to continue my research on mechanical behavior of materials because this mechanical behavior of materials will simulate the manufacturing fabrication method to be applied. So I intend to continue working on mechanical behavior of materials, okay, in terms of finding the contact, fatigue, deformation, fracture, and the structure property processing performance relationship. Also now relate this mechanical mechanical behavior to manufacturing processes such as additive manufacturing, biomanufacturing, and precision engineering. I also want to continue my research in biomechanics, that is application of mechanics to biomedical materials, and also nanomechanics, that is study of mechanics at nanoscale. So also, I also want to continue in my research in surface science and engineering, that is to find surface integrity, modification of surfaces in order to have improved properties, and so on and so forth. Okay. Specifically, I will not go much into this because I just need to have a general view. But I want to keep some ideas to myself. But because I don't want to expose everything that I'm doing currently. So my future research now in broad view now are one, I want to continue with the prediction of mechanical behavior of material using artificial intelligence method. So artificial intelligence based material engineering, focusing on structural mechanisms, material selection, and the material discovery for engineering and medical applications. That is one. Two, I want to go into additive manufacturing of biocompatible ceramics for engineering and medical applications. Also, I intend to research on design of bio-inspired structural materials for dental, medical, and engineering applications. Then I also want to investigate nano machining induced surface and surface damage of potassium dihydrogen phosphate for high power laser system. Potassium dihydrogen phosphate is a soft and brittle material, but it has found a wide usage in energy application and also in high power laser system. So I just want to go into that. So this one can be a research topic for my future PhD students. Then I intend to investigate thermal cycling behavior of dental ceramics using mouth-to-mouth chewing simulator. Then the mechanics of kink banding discovered for princeton zirconia also needs to be elaborately investigated further. Now, based on my research that I've done, spanning about 10 years now, I've received numerous awards, including in 2021, Elsevier Reviewer Award certificates in recognition of excellent reviews that I performed for several journals. The most notable award that I received was the University Medal for Excellence for a doctoral research thesis at the James Cook University, Australia in 2016. The College of Engineering comprises mechanical engineering, civil engineering, electrical engineering, and computer engineering. And I was the only person in the whole College of Engineering that received this medal during my convocation in 2016. Then, for my study at James Cook University, Australia, I also received international research scholarship for the PhD program at JCU, Australia. My master thesis at International Islamic University, Malaysia, okay, also received gold medal at the Faculty of Engineering Research, Innovation, and Exhibition in 2006 for the project titled Surface Finish Prediction Models for Precision Grinding of Hard and Brittle Materials. Then also I've received grant for this project, development of durable, aesthetic, and biocompatible ceramics for dental restoration in my present working place, that is University Technology Brunei Research Grant. Okay, so these are the research awards. You can see excellence, yeah, excellent doctoral research thesis, James Cook University, and this is my name written on the other side of this. Okay, these are the review evidence of reviews that I did for the Elsevier, and this is a recognition letter, and this is the certificate of the award of gold medal. Okay, my teaching experience spans more than 8 years in universities in different continents in Asia, Malaysia, Saudi Arabia, Australia, Oman, and Brunei Darussalam. My teaching experience started as with the teaching assistantship offered at the International Islamic University, Malaysia, for 3 years, where I tutored statics and mechanics of material. Then, after that, I proceeded to International University College of Technology, TwinTech, for about 1.5 years to teach computer-aided design, computer-aided manufacturing, project management, manufacturing technology at the institution. Then I was a lecturer B at King Fahd University of Petroleum Minerals, Saudi Arabia, for about 2 years or 2.5 years, teaching material science and mechanical vibrations. Then thereafter, I moved to Jubail University College as a lecturer, also in Saudi Arabia, for about 1 year, teaching statics, dynamics, and mechanics of material before proceeding for my PhD at James Cook University in Australia. While at the James Cook University in Australia, I was a lecturer for about half a year, demonstrating material science because of the involvement in my PhD thesis. So I did not have much time to do to teach. So I devoted most of my time to my research. That was why I was able to finish on time, and I was able to publish so many papers. So after my PhD at James Cook University, I had a brief stint at the Ton Doc Tang University in Vietnam as an international researcher. So doing research for them. Then I moved to Oman as a senior lecturer at Middle East College in Oman for about 1 year, teaching fundamentals of mechanical engineering, industrial project management, stress analysis, that is talking about elasticity, plasticity, and then fracture mechanics, also materials and manufacturing. Presently, I joined University Technology Brunei in 2019 as an assistant professor. And now I've stayed here for about 3 years now. So I've been I've taught several undergraduate subjects, including manufacturing engineering, computer-aided manufacturing, industrial automation and control system engineering materials. At the graduate level, that is the Master of Science, Mechanical Engineering coursework, I've been able to teach material failure analysis and prevention, manufacturing technology management, and engineering optimization. That is talking about the design of experiments, artificial intelligence methods, and so on and so forth. Okay, the teaching methodology that I've been able to use are the traditional face-to-face method, then project-based learning, team-based learning, flipped learning method, and research-led teaching, electronic learning. So in my future video content, I'll be able to expand more on all these teaching methodologies. So I advise, or in order to improve this or to continuously improve the creating videos, I urge my viewers to subscribe, to like, and share my YouTube videos, because it is time consuming to make a video clip. Thank you very much. I'll see you in the next video. Please subscribe to my YouTube channel for interesting video content bordering on science and engineering, education, and research. Thank you very much.